Today I'm going to be sharing with you a super interesting topic about the generation of explorative maps using explorative geological maps, if we want to, using unsupervised learning. So I'm going to start with a brief explanation about what machine learning is, and specifically I'm going to be talking about the unsupervised learning. Then I'm going to pass to the case study. So first, I'm going to open with the scientific questions behind this research, and then I'm going to illustrate you the case study, the workflow, the results, a little bit of the discussions, and about the ongoing work. So machine learning, we've all heard many definitions of machine learning and AIs. And a definition that I really like because it really represents what is behind the algorithms is that machine learning is just statistics on steroids, lots and lots of steroids. But at the end of the day, it's just like super high level, let's say, statistics. Here you can see a chart of the different machine learning concepts and the taxonomy, going from the supervised learning and the unsupervised learning, which are under the more mathematical point of view of all these different techniques using mainly calculus, linear algebra, and statistics. And then you have the model-based kind of approaches, including the reinforcement learning, deep learning, and ensemble methods. This was just a blank space that I need to fill on my slides. So today I'm going to talk mostly about the unsupervised learning, but I'm going to show you a little bit about what a supervised approach is also. So for the supervised approach, let's say that we have as an input data, we have label data. In this case, we have cats, and we have three different categories of cats. We have a cat in a box, a crying cat, and a cat eating pizza. So what can I do with this data? For the model training, I use this label data, which is my training set, and then I put a little portion of this data set into hold, okay? I take it aside for the evaluation step after. Then the model learns the patterns from the data using different algorithms. And these algorithms decide in which way you can rearrange the data to fit your training information. Okay, so you can use support vector machines, decision trees, k-nearest neighbor approaches, and even neural networks. Then during the processing, what you do is that each algorithm tries to minimize the errors between the model information and the training information. And at the end of the day, you have a model that can be used for making predictions on new data. And this model will be tested, okay? The performance will be evaluated on that holdout set. So the information that you took apart from your training set that you set apart for evaluation. So you will be able to establish different metrics, such as the accuracy, the purity, the F2 score, and many others that will help you to numerically assess the performance of your algorithm. And after that, after evaluating your model, you will be able to do predictions on new unseen data. Okay, this is just a summary of what I've just said. And with regards to the more mysterious unsupervised learning, let's say that our input data in this case is raw, unlabeled data, okay? And in this case, I maybe know they are cats or maybe I don't. I can have a general knowledge about my data set or I can know nothing, okay? So for the model training, or as I like to call it, the model fitting, okay, because you're not training since you don't have a training set, you're working with your unlabeled data, okay? You do the same thing as in the supervised learning. You take a portion of the data of this data set for evaluation, okay? And then you use different algorithms that will have the task to learn the different hidden patterns between within your data set. Okay, you can use approaches such as k-means, Gaussian mixture models, dbScan, and other clustering algorithms. So during the processing, all these algorithms will try to group the different data points of your data set based into similarities, okay? If 2 points are similar, they're going to be grouped together. And after that, the result will be a set of clusters, okay, or groupings that will represent these patterns on the data. For example, in this case, all the cats within a box will be clustered into the cluster C, for instance. The cats that are eating pizza will be classified into another group, and so on. Of course, if you do not have knowledge about what you are classifying, you're going to simply have, for instance, cluster A, B, C, and so on. Since you usually do not have a knowledge of the ground truth, so of the label data, you can use intrinsic methods for evaluating the performance of your clustering. And these methods are based on trying to figure if your distributions, if your cluster are homogeneous enough, if they are well separated within each other, etc. But if you do have knowledge of a portion, for instance, of a labeled data set of your data, you can use that information to do a partial evaluation of your data set, okay? And with this ground truth, you will be able to evaluate the different metrics, and so a numerical evaluation of the performance of your model. So after that, your model will be ready to discover hidden patterns on new unseen data. So I'm going to go very, very, very quickly on the most, the classical clustering algorithms, which are the k-means, the Gaussian mixture models, and the dbScan. So the k-means is a centroid or distance-based algorithm. Okay, so you start from a random distribution of points, okay? Then you need to decide, in this case, the number of classes or clusters you want to find. And it works like this. So you first put a random point, okay, on your distribution, which are called the centroids. And then each data point, it is assigned to the nearest centroid, okay? So this is the expectation step in which I expect that, for instance, this point will actually belong to this centroid. Then I move towards the maximization step, in which I try to maximize the likelihood of the cluster representing its points. Okay, so I recalculate the mean of these points and I reposition the centroid. Okay, so going back and forth between the expectation and the maximization steps, I will arrive at a point in which my centroid will be not move anymore. And so that is to say that my model reached convergence, and you will have the final clusters. In the Gaussian mixture models, instead, you assume that the distribution of your data is distributed in a Gaussian, so in a normal distribution. And a normal distribution is characterized by different parameters such as the mean, the covariance, and the weights. But we do not know these parameters before, okay? So with the Gaussian mixture models, using always also the expectation maximization principle, you first calculate the probability that a certain point belongs to a distribution. For instance, this point here has a 70% probability of belonging to the green bell and a 30% probability of belonging to the red bell. And this is the expectation step, okay? Then you go to the maximization step, which in this case, it is the refit, okay, the reshape of the bell based on the new distribution of these points. So you recalculate the mean, the covariance, and the weights, okay? So going back and forth again between the expectation and the maximization steps, at a certain point, your parameters will be stabilized. And at that point, you will have your clusters. There's a third method, and I'm going to go very quickly with this one, which is a density-based kind of algorithm, which tries to cluster the different your data based on density metrics. Okay. And the cool thing about this kind of method, it is that it allows you to recognize noise. Okay, so in this case, not each point will be assessed to a cluster, but instead some of the points will be recognized as outliers or noise points. Okay, so it is a really powerful technique when you want to assess the noise or the outliers of a data set. Now, I prepare for you a quick pop quiz. You can scan the QR code very quickly. Please let me know, even the other speakers can let me know if they can read the QR code.
Is reading fine?
Okay. Can you see the form?
Yes.
Okay, you have 2 minutes. Okay, so I will show you the answers. There was supposed to be a timer, but it's not working. Okay, these are the answers to the question. So regarding to the first question about the goal of the supervised learning, well, the goal of the supervised learning is to learn from labeled data to make predictions. There was a 79% of right answers, so it was really good. Then the main objective of clustering in unsupervised learning is to group data points into clusters based on their similarities without using labels. And you got that, this one right, almost all of you. And then there was a little bit of different opinions on the last one, but the true statement on the last question is that the Gaussian mixture models assume that data are described by a mixture of Gaussian distributions, and then you use expectation maximization algorithm to obtain the parameters. Okay, so thank you for your answers. And now we can go towards the second part of this presentation of this seminar, about the generation of these maps and about the questions behind, like, why do we need, for instance, to create more advanced methods for cartography? Okay, so we know that the geological maps, both on Earth and in planetary surfaces, are great tools to help us understand, for instance, the formation history of a planet, the different surface processes such as volcanism, tectonics, and so on, and also the compositional variations, for instance, the lithology. And all this information together can have a practical use. They can be used, for instance, for the identification of potential landing sites or for the planification of exploration missions. But the creation of such maps requires, well, they are highly complex, and they are highly complex because our input data, it is already complex, because maybe we do not have the right resolution, we have low resolution data because they are complex to interpret, because we do not have the same features as we have on Earth. Okay, then it is a time intensive task. And last of all, the creation of such maps requires the specialized knowledge of an expert. And because of this, it may be subjected to an operator bias or to a subjective interpretation, because maybe the cartographer has a personal interest, scientific interest into finding something, or maybe because of his background or their experience, okay? So it can be subjective. And another issue related to the generation of these maps is related to the way in which we build them. It is almost often based on a geomorphology approach. And the spectral information, it is just used to, for instance, help us redefine the limits between the different units, for instance, for the hollows or other surface features. And here you can see an example. This is the Rachmaninoff basing from the H05 quadrangle of Mercury. This is the morphostratigraphic map. And here you can see the same area, but this map comprehends both the morphostratigraphic and the spectral information. So here you can see a more refined and a more robust information with all the different lithologies. So this work aims to create a set of global maps, explorative maps, that incorporates both spectral and geomorphological information using unsupervised learning. And we use unsupervised learning, as I said you before, because we do not need to train a model, okay? So the ground truth, it is not necessary. And this is important because we know that we have certain rules for mapping, okay? But it is always a work subjected to the interpretation of the operator. So we can have, even on the very same area, we can have two different geological maps if we put two persons to do the same task, okay, because of the different interpretations. Here, for instance, if we compare these two quadrangles, okay, the H06 and the H10, okay, they're adjacent to each other. If we go to see the union between these two maps, we can see that, for instance, the operator in B interpreted this zone as intercrater plains, while the operator in A interpreted the same terrains as intermediate plains, okay? There's also a difference between the ratio of the ejecta and other, for instance, in stratigraphy. So in the work of trying to merge all of these different maps, it is a really hard task because you have all these different interpretation. So we think that with unsupervised learning, we can create more objective maps that can aid both the cartographer and the person in charge of merging all of these different pieces. Okay, so this is a workflow that I use for the creation of these automatic maps. Starting from the data set, I use the DEM as a morphological base and the A-color map as the spectral information. Then I created a set of different derivative maps, for instance, the ruggedness, the slope, and I created different spectral slopes for the spectral information. Then I did a balancing of the data set, and I'm going to talk about this in the next slides. And then I proceeded with the fitting using a Gaussian mixture model. Then we went on the evaluation and the test of the model. So each fitting step was made on different cubes. Each cube contains different layers of morphological and spectral information. And each one of these packages, these cubes, was fitted in 4 different configurations, using, for instance, normalized information and not normalized, or balanced and balanced information. Then we use 80% of the pixels for doing the fitting, and at 20% of the pixels, so a holdout portion, for the evaluation. This is the balancing process. As you can see here, the smooth plains occupies almost the 50% of the pixels in this image, while the crater floor materials hummocky occupies just a few pixels. So if I do the fitting on this information, because I know in this case the ground truth, okay, I'm going to be my model will be super efficient in recognizing the smooth plains, but it will be not that efficient on recognizing the other different units. So you do a balancing in which, as you can see here, the green bars are the data before the balancing. So these are the smooth planes in which I have almost a 50% of the pixels of the whole image. And after the balancing, so you have to see the blue bars, we could make a more homogeneous input data set for the fitting. This is just the visualization of the balancing on the ground truth that we have in this case study. And these are the results related to the fitting. And as you can see here, we have all the 4 configurations with balanced and normalized and not normalized data. And as you can see from the results, you can distinguish very well the limits between the different units. For instance, in this case, between the smooth planes and the intermediate and the intercrater planes. You can recognize the borders of the different craters as well as their ejecta. And you can recognize also some information on the surface features such as the pyroclastic deposits and also the bright materials. So if we do the evaluation of this information, okay, because we have the ground truth, so we can calculate metrics. In this case, we can see that this model is very efficient in recognizing the smooth planes with a high accuracy. But for instance, if we look at the intermediate planes, if you just look at the accuracy, you could tell, okay, this is good enough. But the other metrics indicate that there's a high number of false positives, so pixels that do not belong to this class, okay, to this unit. And this is visible from this histogram, okay, in which you have the number of pixels per the different geological units. And as you can see here, the model is an expert in identifying smooth planes, while you have many false positives on the intermediate planes, okay? And this is all to say that, first of all, not all the predicted classes, okay? So not all the clusters that I obtain from my model could be associated to one class of our ground truth. And this is because the maps that we are obtaining are contain both the morphological and the spectral information. So they are much more informed than the geological map. In fact, if we go to analyze the fitting of the package that contains just spectral information, okay, we see a whole another picture. We know that we cannot compare this information with the geological map because they are different things. But we can, of course, compare this map with a map of the spectral units. This is a map done by Francesca Zambon in 2022. And this contains an analysis of all of the different spectral informations on this quadrangle. This is the Hokusai quadrangle, okay? And so I can compare spectral with other spectral information for evaluate the model. So at the end, we decided to take a different approach. So we are going to start by building just morphological maps using morphological information. And we're going to compare this morphological information with the geological maps. Then we are going to generate a map using just the spectral information, which will be evaluated using the spectral units map. And then we're going to do a merged map, unifying the spectral and the morphological information. And we're going to evaluate this last product by doing a blind test in which a person, a cartographer, will try to map a certain zone of the Hokusai quadrangle by using just these 3 products. And this information is going to be compared with this complex map that I showed you before that contains the lithology as well as the geological units. And after that, after deciding which is the best model, we're going to apply it to a new quadrangle, so a new information to obtain these global unmerged maps of Mercury.